tree of K3, right? That's what we did. The number of spanning tree for n will be same as number of spanning tree for Kn. Okay. Out of these, some may be isomorphic, some may not be isomorphic. So total number of trees are n minus 2. This one. So 3 raised to power 3 minus 2. 3 raised to power 1. That is 3. And you can count it. Right? But what is the problem? Over here, all these are isomorphic. Here, so if we say the distinct or non-isomorphic or up to isomorphism, how many three? Only one. Clear? Every tree, every graph have a spanning tree. Is the statement true or false? Every graph or has a spanning tree.
False, ma'am.
Why?
Disconnected graph can't be a spanning tree.
Yes, so that I have written over here. If you if G as disconnected graph, there will not be any subgraph which is connected, right? That's why this has no spanning tree. Now we will try to count the number of spanning tree, all the spanning tree. We will try to list all the spanning tree for a graph G. And the first example is kite. How many spanning tree? Spanning tree will be connected acyclic and contains all the vertices. So these graphs are containing all the vertices, right? And this one, spanning tree connected acyclic, this one, and this one. This is coming from outer cycle, right? And if you involve this diagonal, then this opposite n type and z type 2 and 2 more, that is K1 3. Okay, clear? So how many tree exist? How many spanning tree exist for kite? How many spanning tree exist for a kite?
8.
8, right? This one, these 4 and these 4. Out of these, how many are isomorphic? Means up to isomorphism, how many? Different.
Three different.
3 different. Which are? These are different. These are same, isomorphic, and these are same. What about these? This is also P4, na? P4. These are P4. These are same as these one. Two different. One is P4 type, another one is K13 type. Is that clear?
Yes, ma'am.
Okay. If I increase one edge, now how many? This is now K4 now, not kite. Now tell me how many spanning tree can you find? Yes? Let's try to list all the spanning tree. See, we have listed all these for kite. So these are also for K4, these 8. What else? See these four containing diagonal. So we have next diagonal this one. So there will be four more containing this diagonal, right? This diagonal plus two edges. This diagonal plus two edges. This diagonal plus two edges. Okay, clear? And four more. The total number of spanning tree for K4 will be 4 raised to power 4 minus into this one. So 4 raised to power 2, 16. List all these 16 in this graph. Yes. How many spanning tree? 16. Out of 16, 8 we have listed already for this one, right? About other 8, yes, draw it, check it. Anyone?
And we can take the first vertex and make one.
Which edge you are talking about?
And from A, K13 we can make.
A2,
K13 we can make.
A13, okay, this one. And this K13.
And one from C.
Yeah. 8 plus 2, 10. About the rest 6. It will be a kind of opposite Z, right? Containing this diagonal, opposite Z and N type, right? So if you delete this one and this one, right? This is N and opposite Z. Two more this type. Clear?
Yes, ma'am.
This will be this to this, this to this, this to this. Four more. Yes? Anyone? Four more. You've listed 12. See, these are the without diagonals, right? These four. These four are containing one diagonal, and these four are containing other diagonal. Now you just take those which are containing both diagonals at the time. Okay, These are zero diagonal. These all 18 are with one diagonal. Now both diagonal. Clear?
DP is
DBAC. This one. ACDB. This one. And BDAC. This one. And ACBD. Clear?
yes, ma'am.
So these 16 will be the number of spanning tree corresponding to K4. Out of these, how many different means how many are isomorphic? How many non-isomorphic tree? These are P4, P4, P4. These are also P4, and what are K1 3 times. So two different spanning tree. Clear? So byte has 8 number of spanning tree and K4 has 16 number of spanning tree. I discussed. Any doubt? Yes. One way is to find the spanning tree. You just draw all the spanning tree one by one and count it. Okay. Another method is to find it by matrix method, and another is by edge contraction method, or this method is also known as recurrence method. Okay. Edge contraction. When an edge contracts, what it forms? Yes. If it will contract this edge, what it will form? Point now. A is equal to B. If it contracts to a point, then it will be A is equal to B and it will be just one point, right? Now, what about you have E1 edge and E2 edge? Here, A to B. You want to contract E2. E2 in a single point. Then what will happen with E1? After contraction A2, how this graph will look like? Yes?
Loop.
Loop. Correct. Right? Even loop will be there and this is getting contracted. So A is equal to B. So like this, we can count the spanning tree for example, by edge contraction, but we will form new two graphs by using G. So we'll transform G into G minus E. We will choose one edge, which is not a loop, it can be multi-edge or simple edge. We will delete it from G and we will contract it in G. And contract, whenever edge contraction is happening, the edge E is getting contracted in the graph G. We denote it by G dot E. Okay, G minus E is the deletion of edge E from G. Clear? So we transform this G into G minus E and G dot E, and then what we do? Count the number of spanning tree. Tau G denote the number of spanning tree. This will be the number of spanning tree for G minus E plus number of spanning tree for G dot E. Clear? How edge is getting contracted? Obviously, you already know that contraction of any edge E is equal to UV is the replacement of this edge point to two endpoints of edge with a single vertex. Okay, U and V will be replaced by a single vertex whose incident edges are the edges other than E that were incident to U or V. So what does that mean? All those incident edges earlier, whatever it was, those will be remaining remaining same except the edge that is being contracted. Clear? E2 को छोड़ के सबकी सब एज इंसिडेंट वैसे ही रहेंगी जैसे पहले थी, राइट? Okay. For example, if you want to contract this edge, this is the graph G. G dot E will look like, so this is getting contracted. U is equal to V. Then what do you got? These two and these two. 4 edges will be adjacent to that vertex. Earlier it was 2, 2, na? Now it is replaced with a single vertex. So this one is happening. Clear? So these forms multi-edges and this forms cycle C3. And earlier it was forming C4, na? And if you contract any edge in Cn, are you getting again a cycle? If you are contracting any edge in Cn, what you will get? Yes?
2 cycle connected with a vertex.
Vertex n minus 1, right? So, two vertex are forming a same vertex. This will be Cn minus 1. Clear? Now there is this formula, this you can remember, I already discussed that tau G is representing the number of spanning trees of G, and any edge E which is not a loop you will take it and then subtract this, delete this from G, get the graph G minus E, and by contracting it with the graph G dot E. Okay, and then count the number of spanning tree for G minus E and G dot E. Those will be the number of spanning tree for G. Clear? Got it? Where G minus E is the graph with deleted edge, and if we contract any edge, then it will be G dot E. Okay. Now for kite, we already know that tau of G, where G is kite, this will be 8 na. Now find this number, that is find tau G, number of spanning trees, by edge contraction method. So by this method, can you find the edge of that is find tau G, that is number of spanning tree. Yes, by using this one only. Yes. Are you getting it or not? We have this as kite, right? You take any edge, this one, or this one, this one. I'm just taking the middle one. This was G. You transform and get the two graphs G minus E and G dot E. Clear? G contracted with E. G minus E will look like C4, na? And for C4, how many spanning tree exist? For C4, how many spanning tree exist? Tell me.
4, ma'am.
4, right? You've done it. Outer C4 will be having 4 spanning tree. Plus U and opposite U, and then left hand side of 1 and then right hand side of 1. That is your C4. G dot E will look like this edge is getting contracted to a point. Then this edge is this one. and these two edges will be incident. This one and these two edges will be incident to this one. Okay, clear?
Yes, ma'am.
So how many spanning tree for G will be according to this one? It will be tau of G minus E. There are 4 spanning tree plus how many spanning tree can you find for this figure? There are 4 edges are present. This one, this one, this one, this one, right? So P3 will work, and how many P3 exist? This edge with this edge, this edge with this edge, this edge with this edge, this edge with this edge. So 4 exist, right? That is these two edges, these two edges, and what else? This one. This edge and these two edges. Clear? 4 number of spanning tree exist and 4 over here. Total number will be 8. You can see it. We have transformed G into G minus E and G dot with E contracted. Now you might wonder that why we are contracting and deleting the edges. After deleting, we are getting the simple graphs, right? More simple graph. Not much complicated graphs. For that, we easily can draw the number of spanning tree. Okay, all the spanning tree and then count it. Clear? And same is happening for edge contraction. Okay. Any doubt?
No, ma'am.
Yeah. Now, someone of you will say that if I don't choose this as E, then you can choose any one of the other, right? Finally, you will end up getting 8 number of spanning tree. So if you just choose this as E, after contracting it, what we are getting, this edge will be parallel edge, this one, and this one is remaining same. Clear? Plus G minus E. So if you delete it, you're getting this K13 and this one, this edge. Okay. Now, can you count the number of spanning tree for this graph? How many spanning tree exists for this graph? G minus E. Just try to find, try to draw. Just tell me. G dot E and G minus E. See, this is a triangle, and whenever any bridge is there, that is any edge which is not present on any cycle, any cut edge is there, that will be present in every spanning tree. You cannot cut it, right? Otherwise, the tree, that graph, the subgraph will be disconnected, and that will not form a tree, right? So this edge will be everywhere, and for this triangle, how many exist? 3, right? So 3 for this one, and how many for this one?
5.
5. So first is this one, means 3 for this triangle.
Yes, ma'am.
These two, and these two, right? And then if you add this edge, outside edge, then 2 more, right? Because this will be common in both triangles, right? So this edge with this edge and this edge with this edge. So 2 more, 3 plus 2 plus 3. How much you are getting? 8, right? The total number of spanning tree you are getting 8. Now, even if you are not able to find over here, that if you are not able to count the spanning tree or this one for G dot B and G minus E at this stage, then again you can consider this as H1 graph or this as H2 graph. Okay, and then again you just apply the recurrence. Okay, edge contraction. Add that is assume any edge that you want to delete it and contract it from the both graph, this one and this one. So first you take this graph H1. So H1 minus E will be this one, right? If you delete it, and if you contract it, then you are getting this figure. Understood? If you delete it, the second figure, and if you contract it, you are getting first figure. Okay, and for the second one, if you delete it, you are getting this figure, and if you contract it, you are getting this figure. And if you look at these two figures, these are kind of same, right? Isomorphic. Clear? So we can write this plus 2 into this one plus this one. So wherever you have connected graph and acyclic, that itself is a spanning tree, not any other. That is having that itself is a spanning tree. Clear? There is only one and only one, or exactly one spanning tree exists for this last one, right? And for this first one, there are 3 spanning tree. One is this edge, one is middle edge, and one is last edge. So 3 plus 1, 4. And for this one, how many exist? There are 2 type of graph here. So 2 into how many spanning tree exists for this graph? One this edge, another is this edge. 2, right? This one, another is this edge. Understood? So 4 from here, 3 from first, and this last one. So how many total? 8. Clear?
Yes, ma'am.
Is there any doubt by counting how many spanning trees there? That is counting tau G. No? Then there is
No.
one more method, that is matrix tree computation. Yeah, this one is again the same thing I have listed. Okay. Here the tau G is the number of spanning tree of G. G minus E is with deleted G, and G dot E with contracted G. And E should not be any loop. You cannot contract or delete any loop from there, because loop anyway will not be the part of spanning tree, right? How many spanning tree exist for this graph? For this graph, how many spanning tree exist? Only 2, right? These 2 edges. Loop will never be the part of spanning tree. That's why we discard it. Okay? Clear?
Yes, ma'am.
Yeah. Now there is one more matrix tree computation. In matrix tree computation, this should be a loopless graph. Okay. In a loopless graph, you have all the vertices v1, v2, and so on vn. You find the adjacency matrix. What about AG? How you find it? Adjacency matrix? Yes. This will be n by n matrix, and this will be symmetric matrix. Here are the vertices, here again vertices, and number of edges between ith vertex and jth vertex, right? That will be your Aij. Clear? Number of edges with endpoints vi and vj, and this will be symmetric matrix. Clear? Because number of edges here we are having undirected graph. Okay, so number of edges between Vi and Vj will be same as Vj and Vi. Okay, so from this graph, from this matrix, what you do? We will form one more matrix named as Q. Okay, that will be containing Qij. Now, in this matrix, what was the diagonal entries? Diagonal entry in Aj,
0, ma'am.
zeros, right? So, by taking all these Aij, Qij as minus Aij, okay, Qij as minus Aij, and at diagonal entry, you will be taking the degree of Vi. Okay, that is this one. For I is equal to j, that is diagonal entry, you will write degree of Vi, and for non-diagonal entry, you will write minus of Aij, that is minus of number of edges between ith and jth vertex. Clear? Hmm? So finally, you got this Q. You can write this AG or not. Okay, that's up to you, because finally you need just Q, and that is based on AIG. Okay, and AIG is same as we define in adjacency matrix. Clear? So we found this Q with Qij. Qij at diagonal entry is degree of ith vertex, and non-diagonal entry is minus of Aij, that is minus of number of edges between ith and jth vertex. Clear? Then from this matrix, this will be again n by n cross n. Again find one more matrix, that will be Q star, and how? Delete one row and one column. Any row and any column you can delete it, but one at a time. Okay, one row and one column simultaneously delete it, then you are getting Q star, and determinant of Q star will give you the number of spanning tree. Clear? Okay, this determinant can be negative or positive. If it is negative, you can take the modulus of that. Okay, that will give you the number of spanning tree. Clear? So first find Q by this method, then find Q star, that will be n by cross n by 1 cross n, that is n minus 1 cross n minus 1 on the matrix. Okay, and you delete ith row, jth column. For example, you are deleting first row and first column, then its determinant will be your tau g. Why it's determinant? In general, the formula is if you delete one row and one first row and first column, that is minus 1 raised to power 1 plus 1. This is for row, this is for column. If you are deleting first row and second column and first row, then what you do? 1 plus 2. In that sense, determinant will be negative. So negative from here, it will finally make it positive. Clear? So in general, the formula of tau g, the number of spanning tree, is minus 1 raised to power I plus j. That's up to you if you want to remember it or not. This is determinant of this Q star, what you got from Q. Okay, if you are getting negative, then take the modulus. If positive, no need to take the modulus. Okay, clear? So what we did in matrix tree computation or matrix theorem, this is again the matrix theorem. The statement is this one only, that if you have these loopless graph, then you have with the Vg as vertex set, okay, and Aij denote the number of edges between Vi and Vj. Then let the matrix Q star, that is Q star can be obtained from Q. Q is Qij n by n, and Qij is the degree of Vi for diagonal entry, and at non-diagonal entry minus of Aij, and minus of Aij is coming from minus of this one. Okay, and Q star is obtained by deleting ith row and jth column. Any row and any column you can delete it. then number of spanning tree for that graph will be minus 1 raised to power I plus j, determinant of q star. Clear? We already know about the kite. Okay, so we can apply this. Now I will just take in this diagonal. So diagonal changing doesn't matter. Number of spanning tree will be 8. First method is this one. You draw all the spanning tree and then count it. Right? Another is by edge contraction method. This one, right? 4 plus 4. That is 8. 8 number of spanning tree. Clear? Okay? For this graph. And matrix tree computation is you just write the degree of every vertex. So for 3, degree is 3, 3 number of edges coming out or coming to the vertex. For B it's 2, for C it's 3, for D it's 2, right? Then find the Q. Q matrix is at the diagonal entry, these will be your degrees, and the non-diagonal entry will be minus the number of edges between ith and jth vertex. For example, this minus 1 is number of edges between A and B. So how many edges? 1 and minus of that. Similarly for C and D. Okay. C there is 1 edge minus 1, and D also there is 1 edge, that is again minus 1. Okay. Like this you can calculate B, C, D, these edges and delete any row, any column. So here I have deleted first row, first column. So that minus 1 raised to power 1 plus 1, this will give you 2, and this will be neutralized minus 1. Okay? Clear? Q star you are getting as I deleted first row, first column. Okay? You got this one. Now determinant of Q star and minus 1 raised to power will be even, so nothing changed, right? Finally, you are getting from this matrix is determinant is 8. Clear?
Yes, ma'am.
So finally, again you are getting 8. 8 by this one, 8 by this one, and 8 total number of spanning tree we have completed. Okay. Now this matrix tree computation is useful when you have at most 5. N is equal to at most 5. Okay. Why is it so? N greater than equal to 5, or you can just say n greater than equal to 6, it will be very difficult to find the determinant because this is coming from the determinant now. So if it is 7 by 7, 7 by 7, then what will happen in Q star? This will be 6 by 6, right? So now you need to find the determinant of 6 by 6 matrix, right? That will be very time taking. So for more than 5, or you can just say more than greater than equal to 6 number of vertices are there, then you can always try it by using this method, edge contraction method, recurrence method. Clear? Yes?
Yes, ma'am.
Next is count the spanning tree in the following graph. In this one. It's up to you. You can also use the matrix tree computation, that is your exercise. Okay? You just try to do it. Try to calculate the number of spanning tree by matrix tree theorem. Okay? Got it? Now by edge contraction, what we do? Yes? we transform G into G minus C and G contracted E. And then we check whether we are able to find the number of spanning tree for G minus C and this graph G contracted E. If yes, you just add it. Otherwise, again recursively you can apply this U. Okay. Again transform G minus C to one graph minus, that is G minus 2 edges. Okay. And this will be G dot one more contracted. Clear? Example, for this graph, G minus E is this one. First we have taken E. If you find G minus E, that will be this one. And if you contract it, what you will get? These two will be multi-edges and this outer side part will be triangle. Okay, so that will look like this one. Clear? If you are able to find it this step only, stop it and just write the sum. Okay, but it is very complicated. That's why we have again taken this as, you can take any other. Okay, and remove it. We are getting this one, and what you do? Contract it. After contraction, what you are getting? These two will be multi edges, parallel edges, right? And this is same, and this is same. Clear? What about this one? G minus E. This graph minus this X. Where you go? This one and this one and this one. These two are isomorphic. You can see it. You can check it. Okay. And after contracting, we are getting this one. Here, this X is this one. Okay. This X is this one, and this X is this below part, and these three edges will be adjacent. Clear? Okay, these three will be forming the, it is multi-edge or parallel lines, you can just say. These two are these two, and the third one is this one. Got it?
Yes, ma'am.
So these two are isomorphic. You can take it twice of one graph only. Okay, I taken it. For this graph, you take this edge. Okay, subtract it and contract it. So if you subtract it, you will get disconnected graph, and disconnected graph does not have any spanning tree. We will discard that. Okay, and after contracting it, this will be to this point only. Okay, to form this is kind of kite now, and for kite we already know how many spanning tree exist. 8, right?
8, ma'am.
So for this one and this one, both one, it will be 8. And yeah, here we are subtracting this one, so we get again a kite-like structure and twice of this kite-like structure, right? So 2 outside plus 2 into this. This loop is getting contracted. This edge is getting contracted. If you contract it, the edge with the endpoints of these 2 points will be forming a loop. Okay, this one. Clear? And this triangle is same. And then this one is same. Clear? So this was all about this one. What about this one? What do? You take this edge, first this graph minus this edge, that will be by relating that edge, right? And then contract this one. If you contract it, you will get the structure. Okay. So how many spanning tree exist for these three? These are 3 into 3 number of kite now. So for one kite, how many tree exist? 8. So for these three, it will be, for
24.
these three, it will be 24 plus 2. Here, how many exist? Loop doesn't matter. We will anyway discard the loop while drawing the spanning tree. So one is this one, another is this one, another is this one, and 2 more for this one. Okay, and what else? This one. Okay, and for this one, how many? There are 5 for this one. 5 into 2, 10, and 24 of this type. How many exists for this one? Fix one edge out of this, run over one by one, over 3. So how many?
6.
6, right? And then you fix this one and run over this one, vary these 3. So there will be 6. And how many for this one? Number of edges time, right? We need just one edge that will be forming a spanning tree. So here 1. How many? 24 plus 10 plus 6 plus 1. 34, 35, 16,
41.
41. 41 or 45? How many? So there is one, there is one, not one, on 5. One
That's
means,
5.
yeah, 5. 1 into 5. No? There are 45. Up to this one, these are 40. And for this one, there are 5. Wait. So, kind of this graph, it will be very helpful. Contractive edge contraction or recurrence method. Otherwise, it will be difficult to find because there are many edges, many cycles formed that directly you draw all the spanning tree and then count it. That will be very, very difficult. Yeah, you can also use the matrix tree theorem and the determinant will come as 45. Okay? Clear? We haven't counted any spanning tree for this one because this was disconnected. Okay? And you can see whatever we have discussed. For this is isomorphic to this one, that's why 8. For this one, 5. For this one, 6. For this one, again 5. Okay? And into the number of graphs of the particular type. Now, this question. Consider the following graph. Use the matrix tree theorem to find a matrix whose determinant is tau g. Means you need to find the Q star such that its determinant only giving you the tau g. So, what about tau g? Tau g is given by -1 raised to power I plus j. Okay, so first you will form the Q, right? And then Q star. Okay, in such a way you will delete from Q to Q star in such a way J and J such that I plus J will be even. Okay, you can delete first row first column, first row third column, or second row second column like this. Okay, got it? So I plus j will be even, then -1 raised to power even, that will be reduced to 1. -1 raised to power even, that will be 1. Clear? So that matrix you need to find Q star. Okay. So I'll suggest you that always in almost all the cases you can delete first row and first column, so that 1 plus 1 will give you 2 and minus 1 raised to power 2 will give you 1 only. So the determinant of this matrix Q star will be directly number of spanning tree. Okay, and yeah, first determine the matrix Q star and then compute this one. That means determinant will be same. Okay, giving the tau g. Okay, so here first you find the qj, that is q is qij, qii, that is at the diagonal entry. These are the degrees. You can just see these are the degree. Okay, and non-diagonal entry are the number of edges between A and B, that are 3 and minus 3 it will be, right? And A and C there is no edge. Okay, here to here. That's why 0. A and D there are 2 edges. This is D. Okay, so minus 2. So similarly you can find and then delete first row first column or second row second column, whatever, such that I plus j is even. Okay, so Q star will be that matrix. Clear? This one. Thus that determinant will be giving you tau g. Okay, finally you are getting 106. So total number of spanning tree are 106. Clear?
Yes,
That
ma'am.
is determinant of this matrix. So here completes 2.2. Tomorrow I'll start 2.3, that is optimization and trees. Here till now we were discussing about only spanning tree. Tomorrow I'll more focus about optimization of this one. That is some weight will be assigned to every edge, or some distance or some length to be assigned to every edge, and then we will find the minimum spanning tree. There are many spanning tree exist now. For example, for this graph there are 106 graph spanning subgraph. Okay, spanning tree exists, and out of that which one will be the minimum? So first we need to have the parameter on the basis of that we can determine this thing is minimum or not, right? So in those type of graphs, these edges will be assigned as some length or some time or some parameter. Okay, so that will be denoted as weight of that edge. So whatever the minimum weight tree, that will be known as minimum spanning tree. Clear? Got it?
Yes, ma'am.
So thank you all. I stop here.
Thank you, ma'am.